Have you seen a man walking on a high road before? Normally, he will use a long pole to balance himself. Imagine if there is a bird land on his pole at his left side of his pole. What will he do? He will actually shift his pole on the right side so that he will rebalance himself in order not to fall down. Now, the same thing will happen to a chemical reaction that is at equilibrium. When you change a system which is already at equilibrium, it will shift to the left or right in order to offset the change. Hi, welcome back to Siri Peshara Kimia Awak. In this video, we are going to look at what is Chatelier principle and what is the use of it and how to use it to predict the direction for the net reaction if we change the system at equilibrium. So Chatelier principles actually tell us if we change a system that is already at equilibrium, the system will shift to the left or right to offset the change. Now, what are the types of change that we have here? There may be change in concentration, change in pressure, and also change in temperature. For this video, we are only going to focus on the change in concentration and change in pressure. Okay, let's look at how changing of concentration would change a system at equilibrium. So remember, if we add a substance, let's say A, the system will try to offset the change. So the system will try to consume. Consume means we try to use up a bit of A in order to reduce the amount of A. So let's say we have a equilibrium system, meaning that everything is at equilibrium now. We try to add some carbon dioxide gas. Okay, where is carbon dioxide? Here. So here, this is carbon dioxide. So we add some carbon dioxide. So carbon dioxide will increase. We have more carbon dioxide. So this is not balanced to the system. The system sense it and they will try to have a net reaction that will help to reduce the amount of carbon dioxide. So how can we do that? Should we shift to the right or should we shift to the left? So if you shift to the right, you will produce more and more carbon dioxide, so which is not feasible. But if we shift to the left, meaning that some of the carbon dioxide will be used to produce calcium carbonate. So the carbon dioxide will be used a bit. So when you try to add some carbon dioxide to a system which is at equilibrium, the system is no more at equilibrium and they try to bring down the amount of carbon dioxide by shifting to the left. Okay, so we will have a net reaction towards the left side to consume carbon dioxide. Now what happens if we try to remove some of the amount of A? So this is not balanced to the system. The system try to rebalance the thing to produce more A. So look at the system again. If this is at equilibrium, we try to remove some carbon dioxide. Okay, this is carbon dioxide. Okay, when you remove some carbon dioxide, what happens to the amount of carbon dioxide? It will become less carbon dioxide in the system. So the system will choose either to shift to the right or shift to the left. So what do you think? Should we shift to the right or shift to the left in order to bring up the amount of carbon dioxide? So the answer is shifting to the right, because when you shift to the right, you will produce more carbon dioxide. So the system will come back to the new equilibrium. So shifting to the right side. to produce carbon dioxide. Now what happens if we have liquid? Oh, sorry, this is solid. It's okay. So if we try to remove or add something that is a liquid or a solid, there would be no effect at all. Okay, we will try to look at this one. Okay, if you have a system which is already at equilibrium, okay, so we try to add calcium carbonate, which is solid. This is calcium carbonate, so we add more calcium carbonate. Okay, maybe you would think that, oh, the system tried to rebalance the thing by shifting to the right, but actually nothing happened. Why? Let's look at the system. Remember, when we try to write the reaction quotient is equal to the product concentration divided by product. So this is product, and this is reactant. So we try to write the species, but we only include those which is not solid and not liquid, because the amount of concentration will be the same throughout the process. So if you want to calculate QP, quotient in pressure, we can write the partial pressure of carbon dioxide. We only include this. This is the product. There's nothing at the solid, so we can write 1. So this is actually still equal to pressure of carbon dioxide. Now, we'll come back to calcium carbonate. If we add calcium carbonate solid, will it affect the quotient, which is Q? No, because in the quotient expression, there is no such thing as calcium carbonate. Calcium carbonate is not involved in the expression. So because of this, Q has no change at all, and Q is still equal to K. It is still at equilibrium. So when something is still at equilibrium, meaning that there is no disturbance to the equilibrium system. Unlike the previous 2 examples, where you actually increase or decrease the amount of pressure of carbon dioxide directly by changing the concentration of that species. In this case, if you change the amount of solid, which is not included in the expression of Q, it would not have any effect on the equilibrium position. So there's no change and there's no net reaction. So the system is still happy as it is. Nothing happened. Okay? Now about the change in pressure. Okay, we have 3 scenarios here. First, the most famous one is by changing volume. Okay, we know that due to Boyle's law, pressure is inversely proportional to volume of the container. So if you try to increase a pressure, meaning that you actually decrease the volume of the container, you compress the gas. So if we increase a pressure, the system will try to rebalance the thing by decreasing the pressure. And how to do that? We will shift to the side with less mole of gas. Okay, if I have 2 sides, okay, one side I have more moles of gas. Okay, so remember, if you have many particles knocking at the wall, they will have higher pressure. This is higher pressure. If you have less mole of gas knocking at the wall, the pressure will be lower. So if you want to reduce pressure, we would shift to the side which has less mole of gas. Okay, so it depends on the equation. Okay, let's see. This is the equilibrium system. So we have a container. So we have a chief equilibrium, so this is calcium carbonate. We have some calcium oxide, and we have some carbon dioxide. Okay, so what would happen if we reduce or decrease the volume? So we cut the volume into smaller, let's say half. This is V, this is half V. Okay, what would happen? Okay, this is calcium carbonate, calcium oxide. What happened to the equilibrium now? Will it disturb the equilibrium? When you decrease a volume, what happened to the pressure? The pressure of the gas inside the container will increase because they have a smaller space to move around, so they will knock the wall more frequently. Okay, so this is a disturbance to the system. So what should the system try to do? The system try to bring down the pressure. So how to bring down the pressure? We will know that they will try to shift to the side with less moles of gas. Okay, let's look at this equation. If we have the left hand side, how many moles of gas? Okay, there's no gas here, so 0 mole. On the right hand side, how many moles of gas? This is gas, so 1 mole. So 1 mole of gas. Okay, so which side has less moles of gas? 0 or 1? Of course, it's 0. Okay, so the system will try to shift to the side with less moles of gas, which will bring down the pressure. Pressure will drop. If you keep on shifting having a net reaction to the left hand side. So this is what we meant by shifting to the side with less moles of gas. So for this system, they will shift to the left hand side, and they will produce more calcium carbonate, and we will produce less calcium oxide and less carbon dioxide, because these two has been used to produce more calcium carbonate, and it will bring down the pressure. Okay, then we have the second scenario. We are adding inert gas. You still remember inert gas? Inert gas is a gas that does not react with anything, because they are inert gas. RD. So the scenario is you fix the volume. Okay, we fix the volume. Okay, let's say what is the scenario? Okay, the first scenario, we have calcium carbonate, calcium oxide, and some carbon dioxide at equilibrium. At equilibrium, all these things should be still inside the container. So this is volume, 1 liter, let's say, and we try to add inert gas at constant volume. So volume is still the same. Volume is still 1 liter. We add in inert gas, let's say argon. So we add in argon. So argon knocking the wall. Let's say this is knocking the wall at 2 atm. Okay. So if carbon dioxide has no change due to the question, so they will still knocking the wall at 2 atm. This is, let's say, 1 atm. So we still have some calcium carbonate, calcium oxide. Okay, now let's look at the P total here. P total for the first container is actually 2 atm, because this is due to the pressure of carbon dioxide, 2 atm. For the new container, we would expect the P total should be the pressure of carbon dioxide the partial pressure due to carbon dioxide plus the partial pressure due to argon. This is Dalton's law, remember? Dalton's law. Okay, so this is actually 2 atm and 1 atm. Now the total pressure will increase for sure because you have one extra gas inside the container and the volume does not change. Okay, but does it change the system? The system which is at equilibrium. Okay, we come back to the Q expression. Remember Q? Q, we only look at the product, which is gas, or for a gas is gas. So pressure for carbon dioxide alone. So if you actually increase or add in argon at a constant volume, we have to check whether the pressure of carbon dioxide will decrease. Will it decrease? Yes. No, sorry. It won't decrease because the volume is still the same. Remember, pressure PV equal to nRT. So pressure for carbon dioxide is actually equal to mole of carbon dioxide RT over V. So mole we did not change. There are still, let's say, 2 mole here, no change. R is a constant, gas constant. Temperature, we did not change the temperature. Volume, we did not change the volume. So basically, if you add in argon, it will not affect the pressure, partial pressure of carbon dioxide. So there's no change to the Q. So Q is still equal to K. Meaning what? Meaning that there is no effect on the equilibrium position. So no shifting, nothing will happen because the system is still at equilibrium according to our expression of Q. Now we have another scenario which is adding inert gas, but this time we have to fix the pressure, okay, at constant pressure. So let's see what is the scenario. Very quickly we draw this again. Carbon dioxide, initially we have V equal to 1 liter, 2 atm. Total pressure is due to carbon dioxide, 2 atm. Okay, let's do this now. Let's say it's the container. We have calcium carbonate, oxide, carbon dioxide, 2 atm. Okay, we put in an argon gas. Argon. Okay, so argon, let's say 1 atm. So P total, we know it would be equal to the pressure, partial pressure of carbon dioxide plus the partial pressure of argon due to Dalton, and should be 2 atm plus 1. But the question says we have to fix the pressure. What do you mean by fixing the pressure? Just now the pressure was 2 atm. So now you must make sure this is also 2 atm. So that this is what we are talking about. Constant pressure. We need to fix the pressure at 2 atm before and after adding the argon gas. Now, how can this happen? It can only happen if this 2 pressure is no more 2 atm and 1 atm. It should be lower than 2 and 1. So what can we do to lower the pressure of gas? So if you remember Boyle's law, the easiest thing to do is to increase the volume. So for this case, actually, we need to increase the volume. The volume can no more be 1 liter, let's say 2 liter. When the volume is 2 liters, the pressure will drop from 2 to, let's say, 1 point something, and this one will drop to 0 point something. Because of this, you can fix the pressure to be at constant pressure of 2 atm. So what actually have adding inert gas at constant pressure do to our equilibrium system? It actually drops the pressure of all the gases. So when this happens, remember, if you drop the pressure, the system try to do what? The system try to increase back the pressure. So what can we do to increase back the pressure? As we have learned in the first scenario for pressure, we try to shift to the side which has more moles of gas. Okay, because when you have more moles of gas, they will knock the wall more frequently and increase the pressure. Okay, let's look at this equation. Okay, this system at equilibrium. Which side has more moles of gas? Okay, the left hand side we have 0 mole of gas, no gas here. Right hand side we have this is not a gas, this is gas, 1 mole of gas, 1 more. So 0 and 1, which side has more moles of gas? For sure is 1. So we will shift to the side with more moles of gas. Okay, so this is the third scenario. Okay, let's try to test yourself after you learn all this. So we try to attempt this question. What would be the following changes? How would be the following changes affect the amount of hydrogen gas in the equilibrium system? Okay, so you can pause this video for a while and you can resume the video after you are ready to check with the answer. So this is the answer. Okay, if you look at the first scenario, if we add more methane, if we add more methane, so CH4 we have more. So the system try to do what? Try to reduce by shifting to the left hand side. So when you shift to the left hand side, what happened to the amount of hydrogen? The amount will be higher because more and more hydrogen gas will be produced. Okay. About the second scenario. Second scenario, if we remove some carbon, okay, this is carbon. If you remove some of the carbon, so the amount of carbon will be less. So how to re-achieve equilibrium? Oh, so sorry, this is solid. Okay, solid means nothing will happen. So nothing will happen. No change. No change. Because solid, right? Solid does not affect the system. Because if you look at the Q is actually product of concentration divided by reactant concentration raised to the coefficient. So if you remove carbon, which is not included in the expression, so nothing will happen. I'm so sorry about this. It's okay. Okay, then we have the volume. If we reduce the volume, what happen? We reduce the volume. Okay, reduce the volume will actually increase the pressure. Okay, so Q equal to pressure of product divided by pressure of reactant raised to the coefficient. So if we reduce the volume, everybody will have an increase in pressure, but this one has more increase in pressure. Okay, so this one will increase a little bit, this one will increase more because of the coefficient square, so it will increase double. If you increase one time, this one will increase twice. Okay, so the Q will be smaller. Q smaller than K. Okay, So if Q smaller than K, they will shift to this side. This is towards the products. This is towards reactants. So if you increase the pressure, the system try to reduce the pressure to be easy. Reduce the pressure. So move to the side with less or more moles of gas. Less mole of gas. Good. So which side has less mole of gas? This one has 1 mole. 1 mole. This side, how many moles? This is not gas, so we have 2 moles. 2 moles. Which side has less? The right hand side. So right hand side. So what happened to the amount of hydrogen? Hydrogen will be lower. Okay, adding neon gas without changing the container volume. Volume no change. So pressure also no change. Okay, so remember, if pressure no change, nothing will happen. So the amount will be the same. The hydrogen would have the same amount. How about adding neon gas without changing the total pressure? Means the total pressure must be the same. So in order to make sure the total pressure is still the same with a new gas inside, we actually bring down the partial pressure of each gas. Okay, so if you bring down the pressure, so the system try to increase the pressure by shifting to the side with more moles of gas. So which side is more moles? 2 and 1. So the left hand side. So if you shift to the left hand side, the amount of hydrogen would be higher. So in this video, we have learned about Lee-Chatelier's principles and how a system at equilibrium responds to the change in concentration and the change in pressure. I hope you like this video. If you like this video, please like, share and subscribe. Thank you.